Hello everybody, this is Mr. Kusaj, and we're up to chapter 2-4, zeros of polynomial functions. Don't forget to put today's date there. Now remember what zeros means. Zeros means the x-intercepts, right? Polynomial functions are these long expressions, so we want to know about the x-intercepts of a longer polynomial function. Well, there's a theorem, a rule that lets us narrow down the possibilities. It's called the rational zero theorem. Now remember, rational means just that, as opposed to irrational, square roots, right? So we're talking about rational zeros, where you can write it down as a fraction or a whole number. We're not talking about the irrational. So here's what the theorem, the rule says. If you have now you're going to see a lot of letters because we haven't gotten to the numbers yet. If you see a long polynomial, right? It starts with some high degree and it goes all the way down to a number without the x, right? That's how they usually go, right? So this rule says that you can take the first coefficient, the first number you see in this long polynomial, and the last number you see, the first number you see and the last number you see, and work with those two numbers and figure out the possible zeros, rational zeros, right? So possible rational zeros are this number over this number, where those numbers, P and Q, come from the first and the last factors, right? So if let's slow down. It's so if you take this number and think of all the factors of this number, you'll have a list, and you put that list on the top of the fraction bar, and then you take this number, think of all the factors of this number, and you write those factors in a list on the bottom of a fraction bar, and then it's positive or negative all those factors, okay? So the P number comes from the factors of the last number in your polynomial. The Q numbers, the bottom numbers, come from the factors of the first number. So it's kind of like the opposite. The top numbers come from the factors of the last number. The bottom numbers come from the factors of the first numbers. You know, now that I'm like saying and listening to myself, it sounds like really confusing, but it's very easy. Remember when I said when we have to write down what the rule is, it can be sometimes a longer explanation than what we actually have to do. So let's look at an example. List all the possible zeros, then tell which one are zeros, if any, right? So these are possible zeros. It doesn't mean that they are zeros. It doesn't mean that they work, right? But this is possible zeros. So here is my function. Notice, this is an easy one. Notice that my first coefficient at the beginning is 1 and my last one is 1. So what my theorem says is that the possible zeros are plus and minus, positive, negative, all the factors of the last number. Well, the last number is 1. The only factor of 1 is 1. Okay? Now let's do all the possible zeros. All the possible factors of the first number, which is 1. Again, there's only one factor of 1. 1. So we have to take positive, negative, all of these factors, positive, negative, all these factors, and put them together. So if we take positive 1 over positive 1, we have 1. If we have negative 1 over negative 1, it's still 1. If we have positive 1 over negative 1, it's negative 1. So if you look at all the combinations here, these are your only possible zeros, 1 and negative 1. Okay? If you still don't get it, I still got 2 more examples. You will get it. Hang in there. So these are possible zeros. So what that means is that these could be x-intercepts for our function, right? We don't have the graph, but we know that these are possible x-intercepts. So let's check. Now remember what we said in the previous lesson? We said that if you plug this in and you get a 0, then you know that this is an x-intercept. So let's plug these in here. We want to know which are zeros. So if you plug in 1, f of 1, you get this, this, this. You do the math and you get 4. Nope, it's not a 0. Okay, let's try negative 1, f of negative 1. Right, I'm plugging in negative 1, right? I do the math, I get negative 2. Nope, it's not a 0. I guess for this function, there are no rational zeros. There could be irrational zeros, but our rule only deals with rational zeros. Okay? Let's do it again. This time there'll be some yeses. So, find the possible zeros using our rule, our theorem, for this function. Okay? So remember, we deal with the first coefficient we see, which is 1, and the last coefficient we see, which is negative 9. Right? So we're going to put all the factors of the last coefficient on top, all the factors of the first coefficient on the bottom. So isn't this right? The factors of 9 are 1, 3, 9. The factors of 1 are just 1. And now I take all the possible combinations of this over this with the positive and negatives. So I wrote them down here. So if you think about it, you could have 1 over 1, which is 1, 3 over 1, which is 3, 9 over 1, which is 9. And you got to take the positive and the negative of each one of them, right? That's what I just said. So the possible zeros are 1, 3, 9, negative 1, negative 3, negative 9. 6 possible zeros. 6 possible zeros. Which one of them work? Out of these 6 possibilities, which ones are real zeros? And which ones don't work? So we have to plug all of them in. All 6 of them? Yes. Well, I did them for you. So here is what I got. I'll move it up. So I plugged in, remember, this is our polynomial up here, right? So I plugged in 1, and it didn't come out to 0. I plugged in negative 1, it worked. 3, no. Negative 3, yes. 9, yeah, no. And negative 9, no. So that means negative 1 and negative 3 are zeros. I found 2 intercepts, negative 1 and negative 3. And if you want to take this one step further, if you know that these are zeros, then you know x plus 1 and x plus 3 are factors. Okay, look at the last lesson. We talk about dividing. Is this a factor? It is a factor if negative 1, plugging in negative 1, f of negative 1 comes out to 0, then this is a factor. So we're doing it backwards. We found out that f of negative 1 is 0, so x plus 1 must be a factor. X plus 3 must be a factor. Okay, I know I'm saying a lot, but you should be becoming familiar with all these terms: factors, zeros, etc. Okay, last example. Let's see if you're catching on. The possible zeros, hold on. The possible zeros for this long polynomial. Now, what do we have here? Right? At the start, we have 3. At the end, we have an 8. So what are the possible zeros? Well, we list all the factors of this one on top. So what are the factors of 8? 1, 2, 4, and 8. 1, 2, 4, and 8. What are the factors of 3? 1 and 3. Isn't that what I got here? 1, 2, 4, and 8. 1 and 3. And don't forget, we got to do a positive, negative of each one of them. Okay? So now, carefully. 1 over 1 is 1. 1 over 3 is just 1/3. 2 over 1 is 2. 2 over 3 is just 2/3. 4 over 1 is 4. 4 over 3 is 4/3. 8 over 1 is 8. 8 over 3 is 8/3. All right? I list them all here. And then you do positive, negative, and these are all the possibilities. A lot, huh? Now keep in mind, it's more than you see because it's positive 1, negative 1, positive 1/3, negative 1/3, positive 2, negative 2, positive 2/3, negative, etc., etc. So it's 1, 2, 3, 4, 5, 6, 7, 8, 16 possibilities. Sounds out of control, right? Well, think about it. How else can you find zeros for a really long, imagine this is even longer, polynomial? At least we can narrow it down to possibilities. Okay? So, so here I'm just asking for the possible zeros. I'm not asking you to plug them in and find out which ones are actually zeros. So, we're done. We're done. These are the possible rational zeros. Okay? So, could you do that for next time? So, go all the way, right? You're going to list all the possible rational zeros, right, with the factors of this over factors of this, factors of this over factor of this, and then plug them in and tell which are zeros. Okay? Do your best. We'll start with this when I see you in class. Okay, so I guess I'll see you later for part 2. Bye.